So this is a calculus video. The first example of exponential growth that James Stewart gives in his 6th edition of calculus, also in chapter 3 of his essential calculus, is population growth. So population growth follows a natural growth pattern. That is, the rate of change of population is generally proportional to the amount of the population. It's therefore a differential equation. We can say that the change in population per time is equal to a constant times the amount of population. Again, it's not exact, but it's a general correlation. Now, we can do a little algebra and move the figures around and define this constant as 1 over the population, so the inverse of the population, times the rate of change of population growth. And this K here is the relative growth rate, and it's a constant. Again, the relationship between the change and the amount of population is a linear correlation, goes together. And so this K is the relative growth rate, the percent, say, at which the population is growing. Now, note the role of K here in the light of the previous video. In the previous video, we noted that this particular kind of differential equation, and that's what it's called, again, when you have two different degrees of differential and so forth, derivative, when you have two different degrees in the same equation, the solution to this kind of differential equation is going to always be of the form e to the kt, because e is the function whose derivative is equal to itself. And so if we ask, well, what is k in this? Well, you can see that because the derivative of e to the kt is k e to the t, that k is in fact the coefficient of t in this equation. So we can say that population equals initial population times e to the kt, where k is the relative growth rate. And I've just reminded you of the equation we ended up with at the end of the last video on exponential growth and decay. That is that solutions to this kind of equation are going to be of the form y equals initial y times e to the kt. And what I've done here at the top is shown you that k, the coefficient, the constant, is in fact e to the kt also when you're getting the derivative of it. So this is the form. This is what is the bottom line of all this? The bottom line is this equation right here. Population equals, and this is just a projection. It works in the 20th century. It's a little bit off when you, the example they give in the book is 2020. Well, it's 2021 when I'm making this video. We know the answer. The population is actually less than the example would have predicted. But anyway, population is going to generally equal the initial population times e to the kt, where k is the general growth rate. And I believe that what they found in using 1950 and 1960 as a benchmark, they found that k is about 1.7 growth rate. All right, so this is the example that I was just mentioning in the book. If the growth rate in the late 20th century was 1.5%, starting with 2000, well, it's actually 2,560,000,000. 2,560 million is 2,560. If it was that much in 1950, then we can create this formula for population growth. That population with respect to time is going to be 2,560 in millions times e to the 0.017 times t. And that turns out to be pretty correct for, I think it's 1995. Again, not so great when we get to 2020. Well, this has been on using exponential growth concepts in calculus to predict population.